And welcome to our transportation series of seminars. This is number 4 in our series, and thanks to Robert Wagner for kind of creating this series for transportation. So this one, we're going to talk about electrification, batteries. Our speaker today is Dr. Claus Daniel, and I asked Claus to give me a bio for this meeting, and I thought this might take a little bit too long to go through, so thankfully he gave you the short one. Now, Claus is our deputy director for the transportation program at Oak Ridge, and is also head of our battery manufacturing facility, and leads a lot of our energy storage as well as the materials R&D in our transportation program. And he is also a joint faculty, a part of UT's Bredesen Center, and has a PhD in material science from Saarland University in conjunction with Max Planck Institute. Yes, and he somewhat wrote the book on battery materials, so we're look forward to hearing what you have for us this morning. Thanks, Claus.
Yes. Does this work? Okay. Thank you very much, Ron. He asked for a short bio, so therefore you only got the first 2 volumes of it. So, well, thank you very much for coming. I think this is a very exciting time, and I really enjoyed the first 3 of the seminar series on transportation, and it's a good way for us to sort of get the word out. What are the activities at the lab? And it's going across many organizations at the lab. So I wanted to give you just a short overview of what are the activities we're involved in across the laboratory. And then I want to pick just 2 examples of the research where I'm personally involved in to showcase what are the contributions Oak Ridge is doing to the field of electrification of transportation. You have seen this before. This is just to sort of remind you again on how wide-spun the transportation program in general is, and that we're looking at a large portfolio of technologies to improve our transportation system. What I will talk about this morning is on the front end. I apologize, this pointer here doesn't work well on this screen, so I'll try my best. But on that first portion here, the electrification. And last time you have heard from Buraco Spinacci on power electronics. Today we're going to switch to batteries, these following 2 topics here: advanced battery materials, processing and modeling, and battery manufacturing R&D. Why are we doing this? Well, this is the latest energy use slide for the US I could find. And essentially, if you compare that to some slides I used a few years ago, when you're going back even as much as 10 years, there has been quite some changes up in that top left corner there, but there has no change whatsoever in the bottom right corner there. And if you look there, that is transportation. Transportation is fed still by about 97% off petroleum. Now, one might be okay with that or have a problem with that, but the big issue, really, what that poses, no matter if you believe in climate change or other things around burning fossil fuel, the real big issue I see in there is that you don't have any flexibility. You are bound by that one fuel. If there is some issue happening, gas prices, problems with petroleum supply, things like that, you have no way of changing it. And that's why we see our economy typically being crippled when we have things like Katrina and some refineries are taken out of the equation. All of a sudden you have a shortage of fuel, and we see that immediately in our economy. So really electrifying the transportation sector allows you not only to get away from petroleum, but it also allows you to be completely diverse. So at any given time or in any given region, you're able to change the portfolio of your energy source. So if you essentially look up there, the electricity generation, that has much more different input sources. And those input sources could be changed as we're going forward then. Of these 34 quads of petroleum, in 2012, 22 quads had still been imported. That's another issue as well, right? So energy security, national security is really a big deal there. Now, but why can't we just electrify all the vehicles and we're good? This is the problem. Right? If you want to put anything else in that car but batteries, we've got to have some improvements. We've got to change things. Another big issue is cost. This is essentially, if you look at a 2011 model year of two vehicles, essentially the same vehicles, if you will, Chevrolet Volt and Chevrolet Cruze. Chevrolet Volt is a plug-in hybrid electric vehicle. The Chevrolet Cruze is just a regular gasoline cousin. You look down there, 5-year ownership, excellent. It's the same. Hooray, we're done. We can all go home, and we're happy with where we are, right? But look at this. You're not making your decision of buying a car by the 5-year ownership cost. At least very few people do that. You're looking at the sticker price. This is $21,000. This is $40,000. That is a big issue. That is a big problem we're facing there. And that is, Burak talked quite a bit about the power electronics last time. I will talk about the batteries. All those additional components you're putting into the car, they're expensive, and we don't know yet exactly how they pan out in terms of lifetime. We don't know yet how well they will do as we're moving forward. So I thought I'd steal one slide from the Department of Energy to have a look at cost once we are at the cost side here. This is a simulation from Argonne National Laboratory looking at if we are able to hit the cost targets which we have developed together with the car makers, the battery makers, the national laboratories, and with consumer information about what would be acceptable for a car, then we come up with several modeling scenarios. And what you see here are 4 different types of batteries for 4 different vehicles. You see a plug-in hybrid electric vehicle with a 40-mile range. That's the PHEV 40. You see a range-extended electric vehicle with a 40-mile range. The difference there is essentially in one, you are driving your car on the electric drivetrain until the battery is drawn down to a certain level, and then you switch over to an internal combustion engine to drive your drivetrain, to essentially a mechanical drivetrain then. In the range-extended vehicle, you continue to drive electrically, but you are recharging the battery as you do so with an internal combustion engine. Then there are 2 all-electric vehicles here, an EV100. That's essentially, you could compare it somewhere with the Leaf, for example. And then there's the EV300. You could compare that with the Tesla sedan. The new Tesla sedan has a 300-mile range. Now you see how with an extended range, essentially your cost targets get more and more aggressive. That tells me that the majority of the cost actually in the whole system is in the battery, and we cannot accept those high costs. We really need to draw them down. Now, 2 other things is if you look at all those pretty colors, 2 colors really come out here, and that's the green and the blue. The blue is the materials, which includes the raw materials and the materials processing to get it into the right form. And then green is the manufacturing. Those are the big cost hitters, and they're getting more and more important as all the other things are getting more optimized. There's very little economies of scale when it comes to the materials processing here, for example. The manufacturing of a battery is also very complex, and there's little economies of scale there. And I'll show you a little later a little pictograph on how a battery is manufactured. So ORNL's transportation program is very heavy in both of those areas. But first I want to see how could we solve the issue. One thing of solving the issue is by dealing with energy densities. If you are producing the same battery for the same cost, but you put materials in which can store double the amount of energy, you divided the cost by half, right? Where are the batteries compared to all kinds of other things? You see here, this is an energy density chart. You see here, let me see if I can use the mouse. Probably better. There you go. You see here ethanol, gasoline, LPG, kerosene, all that somewhere around here, right? You see the batteries down here. That's the lithium-ion battery. There's some air battery technologies shown in here. Now, if you look for what's in the battery, right, we're talking about a lithium-ion battery. Here's lithium, if you would essentially just burn it, right? If you look on now, if you take the batteries, so you zoom into that bottom corner there a little bit, we have a large variety of battery technologies at our disposal nowadays. We started out with, we essentially have in our starter battery technology in cars, we have about a 100-year-old technology, the lead-acid battery. It's a tremendous power source, but it's really very limited in energy and in energy efficiency. A round-trip efficiency of the lead-acid battery is 66%. It means you throw about a third of your energy away every time you charge and discharge. As you're going up the ladder here towards lighter and smaller batteries, you see essentially the lithium-ion batteries coming there. Then you see zinc air, you see lithium polymer, you see lithium metal in there. We're not quite sure yet where our other air batteries will end up once they're done, because we're really in the process of doing fundamental research on those. And we don't know yet exactly what all goes into the mass and into the volume portion of that equation. So we can only compare theoretical energy densities of active materials. But we believe there might be somewhere further up there. We have tremendous problems of even recharging them. So it'll be quite a while till they come along. So in the meantime, what could we do in other areas on lithium-ion batteries? And I'll show you two examples of those. But before I go into that, I wanted to show you a little bit on where Oak Ridge is heavily involved. And this is essentially it includes the activities which we fund through the transportation program, as well as some efforts the PIs have proposed to the transportation program. So in the physical sciences directory, we're having substantial activities on lithium metal protection, on lithium sulfur. We have a little bit going on in air batteries and sodium batteries. Those are we're trying to pitch to vehicle technologies to fund them. And then we have activities going on advanced conversion cathodes. In neutron sciences, we're really heavily using neutron sciences for characterization. We have substantial activities in neutron imaging, and we have substantial activities in neutron diffraction going on. In computational science side, we are a big participant of the national, what we call the KBAT program, Computer-Aided Engineering of Batteries. And then Shrikant and his colleagues are also working quite a bit on modeling of systems for understanding performance and understanding safety better. And then in the Energy and Environmental Sciences Directorate, we're focusing a lot on roll-to-roll processing, coding applications, the battery manufacturing science there, and then scale-up of any one activities which are going on in the other directorates there. For example, one activity we're having right now is taking Shengdu Liang's lithium sulfur and see if we can put that into a pouch cell and then do some testing there. These are the main contributors in the program, working quite heavily with us together in physical sciences, in neutron sciences, computational science, and energy and environmental sciences. The total number of contributors is much bigger. These are essentially PIs or people who contribute in a leading role, I would say. This is the program when it comes to research output. In the last 5 years, I just looked up PTS real quick, and I also noticed that PTS is not complete in that regard. But what you see in there, we're at about 200 contributions to the science community in the last 5 years. And this is a program which is, in size, it varies up and down a little bit, but on any given year, it's somewhere around $3 to $4 million on the transportation side alone. So let's go back to the battery manufacturing. That was one of the cost items, and you will see why. Essentially, if you talk to people who manufacture items, it's quite amazing. When they go through a battery manufacturing plant the first time, they typically, the chin falls down, and they're like, this is how complex a battery is. That is amazing. We have 3 big areas there, essentially the electrode processing, the cell assembly, and then once your battery is manufactured, it's like wine making or beer making. It's not done yet. So you go then through formation cycling. That can, believe it or not, typically last anywhere between a week and 6 weeks. So on the electrode processing, it's typically starting out from a powder material. You have active materials, you have binders, you have conductive additives, you throw into the mix together in raw materials, and you process a slurry, which you can then paint onto surfaces, if you will. So you coat those, you dry those, you remove the solvents, and then you have your electrode. Now from there on, it's a very complex way of discretizing your roll-to-roll product, putting it into a packaging, sealing it off, making sure everything holds well. The big issue we're facing there nowadays is that a lot of the established manufacturing procedures are getting much higher scrutiny nowadays because we can't accept the failure levels we see in consumer electronics, for example. Consumer electronics have batteries in them which at most need to have a regular lifetime of, let's say, about 2 years. In a car battery, we're expecting 10 years. That is a huge change. All of a sudden, you are having seals which need to keep water out for 10 years under all kinds of scenarios. In a consumer electronic device, that's less of an issue. It sits much less in the rain. It sits much less at very abusive conditions, and it doesn't last that long. So after that, you go through the formation cycling, where you do passivation of surfaces inside your device. You're forming the final electrodes. You're forming the right phases you need to have to get actually a good performance over a long period of time. So I want to select one particular topic out here, and it's something where we worked very, very heavy on over the last few years. David Wood is leading this effort together with Jean-Lin Lee, and we're having a quite extensive collaboration in that regard with Beth Armstrong and her group in material science. One of the things we're using in electrode manufacturing are solvent-based slurries. It's essentially, if you go back to your childhood, it was much more fun when your dad was painting the living room, because for the next 3 weeks you were high. Nowadays we don't have that anymore. Nowadays everything is water-based, right? Nowadays we're able to make paints which are waterproof once done, but are water-based process as they are being applied. That's exactly what we're trying to do on battery manufacturing. Currently, the typical solvent of choice in battery manufacturing is N-methylpyrrolidone, NMP for short. It's a toxic, expensive, highly corrosive solvent. It is also flammable. So you're adding materials cost to an intermediate product you just throw in and then you take it out again. Your flammability requires all of your processing equipment, all of your roll-to-roll equipment to be explosion-proof. No sparks anywhere nearby your vapors. And then the toxicity requires you to essentially have a distillation plant after your coating line to recoup the NMP out of your waste stream and recycle it. So why was that not a problem so far? So far it was not a problem because the batteries fit in our watches, they fit in our cell phones. They were relative small batteries, relative small amount of material. And this is the way we typically process them. This is the way we started the research, and therefore cost of that item wasn't really a big problem either. Now when you do this, when you put it into a vehicle like that and you want to drive that vehicle very far, all of a sudden this becomes your glove box. And this becomes your distillation facility. So that is really big. So what we're going to do, what we're doing is essentially we just take that solvent out, we throw water in, we do everything. Why does it not work? Big issues with water, with those materials in water, is they tend to agglomerate. They tend to not create a stable dispersion. They fall out of the dispersion, and you have a sediment on the bottom, and you can't really process that very well. You cannot control your particle size very well. You start out with an okay particle size. Once you experience the agglomeration in your system, you have particle sizes all over the place, and most of them too big. So what we were doing is we were essentially looking, how can we make those batteries stay in a suspension there, stay afloat in my slurry. And one key thing to look at is essentially surface charges of those particles. When those particles have a surface charge which is too small, too close to zero, they tend to agglomerate because the van der Waals forces are overcoming the repulsive Coulomb forces. So if you're able to modify that in a way, you can keep them afloat. The way of characterizing that, the way of understanding where is my particle surface in this scenario is measuring Zeta potential. The Zeta potential is that surface charge you're having on your particle, and whenever your Zeta potential is somewhere in this region, lower than 20 or higher than minus 20 millivolts, you're in an unstable region. Your surface charge is not sufficient to repel the particles from each other. Whenever you have charges above 20 or below minus 20 millivolts, you're able to keep them afloat. You're able to keep them apart from each other. What is very important to understand there is where is your absolute neutral point on a pH scale. And that is very key because that allows you to select the right materials to disperse your particles. That's what we call a dispersant. If you go back about 5 years or so, 5 years ago, and you look into the literature, what people had been using is they ignored that point, and they tend to use the wrong dispersants in the processing, and they had a hell of a time to get a stable dispersion. So what we're doing is we're based on that characterization data. We're selecting our dispersants. In this case, we selected polyethylenimide, PEI. We put that in our system. This here is an example of lithium iron phosphate. There's also carbon black and then the binder in there. And we're looking, how can we optimize our particle size? What you see here is the particle size as a function of PEI content. And you see as it goes down with a slight increase in the PEI, you want to keep that very, very small amounts in your material. That is essentially, that's the same technology which keeps your shampoo from having the soap in the water rather than all on the bottom, right? Things like that. So now the next big thing is, we all know that metal surfaces don't like water very much. On the aluminum foil, for example, you are having a very, very hard time make a water-based slurry to really wet the surface nicely. You need to wet the surface very nicely in order to have a very good adhesion on your electrode, which really determines your long-term performance of the material. And if you see, essentially, if we measure surface energy of the untreated aluminum foil, we're much lower in surface energy than what the surface tension of the water is. That essentially results in water not wanting to spread out, but water to form droplets and de-wet from the surface. So the slurry is a little better. So if we have all of our material in the slurry, it gets a little better, but nowhere close enough to that we can actually meet these values. So we need to close this gap somehow. So what we did is we looked at in plasma treating surfaces. What an atmospheric plasma gives you when you run that over a surface, it allows to clean the surface. It takes a lot of the I call it goo off, anything which floats around the air and settles on it. You can also controllably oxidize your surface. And you can really dial in a surface energy you need. And as you look here, as we're changing the energy of the plasma we are running over our surface, we're able to go anywhere from well below where we had been before to well above the surface tension of our slurry. That now allows you to completely engineer the system very well. You keep your particle afloat in the dispersion, and you are able then to deposit them very well onto your current collector. And voila, when you do that, you essentially drop down to a contact angle of 0. Contact angle of 0 means you have perfect wetting. You put a droplet on your surface, and it spreads out. Exactly the opposite of what we're trying to accomplish with our superhydrophobic stuff, right? So both of these things together now allowed us to dramatically improve the cost structure, right? So what you're doing is you eliminate your toxic organic solvent. We ran some numbers on there. We believe that step alone is able to remove more than 15% of the full battery pack cost. And that means the big system, it means of a $10,000 battery, you scrape $1,500 right off the back, right? And as you can see here, this data shows essentially where we started out. You don't do anything to your system. You end up with a very low performing battery, very low energy density, and a quick fading mechanism. And as we're working our way up, we're ending up with a very good battery with a very good rate capability. This shows essentially the available capacity as a function of how fast you charge and discharge that system. And then we're able to do that nowadays in large batteries, which actually are needed to show that it can be produced on scale. Now, this is all lithium iron phosphate. If you follow the press a little bit, lithium iron phosphate is having a real hard time in the automotive sector. It's a great power battery, but the volumetric energy density is not that great. And so people are looking towards transition metal oxides for the choice of cathode materials in lithium-ion batteries. So we said, okay, we take the next step, we're going into these materials, and when we show that, we're using the exact same procedure of what we described in our patent application. And we're seeing, are we actually able to hold our claim true that we are chemistry agnostic? Because we're having a procedure on how to get to the right recipe, rather than just patent the recipe. A big question always with transition metal oxides is when you throw them in water, will the transition metals dissolve in the water and essentially exit your active material, and will you harm your material? We showed that's not the case. This is some lithium concentration over a full week here. You get up to about 35 microgram per milliliter. That is acceptable for the lithium. You look for the nickel, manganese, and cobalt. It's not detectable. It's below our detection limit. So we're all set. Everything is good on there. All we need to do is develop our dispersion chemistry again, make sure our material wets it, and we're good to go. So this is the Zeta potential again. You see again that red curve is that unstable Zeta potential where you have some crossing over into zero. When we add our dispersion to it, then we're able to move that curve down and improve it dramatically. And here are data. This is unpublished data. This is data which is very recent. John Lee is currently working on the manuscript for publication on there. But it is dramatic. What we have there is essentially you see coin cells, and then you see 3 amp-hour pouch cells. Those are large format pouch cells then. And on the coin cells, the black curve is the benchmark. That is the traditional NMP processed material. And it's right in the ballpark of where the other colors are, other than one particular set of binders. This is a study of which binders should we use for that material. And we had some problem with one binder, but the other two are right in there. We have no issues. So with that, I want to switch gears a little bit here and go away from the processing and say, if we're able to make it quite a bit cheaper, are we getting there? Maybe not quite. If you're looking at where the Leaf gets you, where the Volt gets you, where the Ford C-Max gets you, in terms of what your range is, what your electric range is, in most cases it's unsatisfactory. That's why we need new chemistries. We believe that with lithium-ion intercalation chemistries, you can make quite some big strides. And this is one particular material which could allow you to do that. These are new classes of cathode materials where we're sticking with an intercalation chemistry where we can put lithium ions into the crystal without much change and take it out, which really makes the lithium-ion battery so efficient. And it has a tremendous capacity if you are charging it to very, very high voltages. 4.8 volts is much higher than what we can accept nowadays for our electrolyte stabilities. But you're seeing current commercial cathodes are in the range of about 150 to 160 milliamp hours per gram. This material lays right here, 232 milliamp hours per gram. But it shows two detrimental things. One is it reduces its capacity as you cycle it. That's capacity fade. That's something we have in the other materials too, and we slowly were able to solve them and to extend the lifetime. But something what this material does is see how this plateau of the discharge curve is slowly dropping and coming to a lower voltage. This is what we call voltage fade. And that is a nightmare for Burak. If he needs to design the power electronics for a charger to measure state of charge of this battery, he has no way of doing it. Because if you look, you never want to discharge your battery all the way to the end of that knee. You want to cut it off somewhere here. And when you look at that, you're measuring voltage, and you believe initially with a voltage of about 3 volts, you're at about 90% state of charge. 90% state of depth of discharge. Now, if you're going back 125th cycle, you're taking your 3 volts there. You're actually there, let's say, maybe about 70 or maybe only 60% depth of discharge because your entire voltage curve is lower than before. So since we're probing voltage in batteries to understand the state of charge, that's not possible here anymore. Now, you can avoid that very, very easily. If you don't charge it up very high, you will never see that fading mechanism. but it's also a battery you cannot use. This is horrible in terms of capacity compared to what we have nowadays. So there's no way around this plateau where we have that problem. So what is happening on there? And I apologize for this really busy slide here, but I thought I'd take that schematic to just give you a little bit of idea on what kind of science do we need to do to really understand what's going on in the inside of the battery. And remember, all of that is in a bulky device. We're looking on the atomic scale now. So you're having a nickel manganese cobalt oxide here, which has a nice layered structure. You have your lithium layer here. Here's all the lithium you can access. Here are all the transition metals, right? In your transition metals, in this particular case, there's also quite a bit of lithium in there too, but let's ignore that for now. You're charging it up, so you pull the lithium out, and you create empty spaces. You create vacancies in there, which allows you to later on put the lithium back for discharging them. Now, the tricky thing is, as you're charging above a certain voltage, all of a sudden other things happen. Not just your lithium ions are getting out of there. You're also releasing oxygen from your oxide layer, from your transition metal oxide layer, essentially. So once that oxygen is gone there, you're having essentially you're creating the opportunity for transition metals to migrate around as well. You're creating vacancies there too. And now all of a sudden, everything gets pretty messy. When you put your lithium back, you might not find the same vacancies you had before. Your lithium might migrate between the layers, and it gets really, really tricky. Now, all of this is realized. You see how it is the same crystal structure essentially here in these pictographs. So that gives us a problem. Typically, the way we can very well look at phases of materials is we use X-ray diffraction. We look at the crystal structure. We can look at average distances of atoms and ions in there and get a pretty good idea. In this case, there's no way for you to see the changes going on the side of the lithium ion because it's so light and the changes it's doing are not detectable with your X-rays. So that's where Oak Ridge's neutrons are coming in. This essentially shows two diffraction patterns. On the right-hand side, you have an X-ray diffraction pattern of that phase. On the left-hand side, you have a neutron diffraction pattern. And on the right-hand side, you say, I have a perfect match. I know exactly what that material is. I can determine my phase. I can determine everything I want. In the neutron side, I look here and I see if I take this pattern, what the crystal structure I've calculated with this, and apply it onto my neutron pattern and simulate that, I have some problems. There are some peaks which don't fit. And that shows the power of neutrons in there. If you zoom in and you look at that peak, if you just take the regular crystal structure, you put it in, you generate a peak where there is no peak in your real data. So here now you can start fiddling around with your structure. You take some lithium ions, you take them out of the lithium layer, you put them into the nickel layer, and you take some nickel ions and you put them into your lithium layer. You start fiddling around with that, and Debashish Mohanty spends hours and hours on doing that by hand. So you're taking your crystal structure, you exchange some ions, you calculate all of your pattern again, you try to see if it fits. And all kind of other things happen in other parts of the pattern, which really makes it tricky. But as I'm, for example, as I'm taking some nickel and lithium and I replace them, I switch them over, that peak gets smaller and smaller as I do that. And we could determine that I have about a 3% swap. So about 3% of my ions are swapped, and I have nickel sitting on lithium places and lithium sitting on nickel places. Now the tricky thing is neutrons are very penetrating. They don't have a charge. They go very deep. That allows us really a lot of that good characterization, but they also need a lot of materials on there. And that's why we are currently on the forefront of doing that research, because materials, the amount of material available cycled on that experimental material is very limited. You need about 1 gram of material minimum I feel more comfortable if we have 1.5 or 2 grams of material. That results in something like, what is it, Debashi, 120 coin cells? So 120 coin cells per sample. That's just unsustainable. You can't do that. And there's where we were fortunately able to create large pouch cells, cycle that material in that more or less industrial size, create enough material of that experimental stuff, and do that characterization. And what we're then able to do is we look into the details of, okay, if we start cycling this material over long periods of time, what is happening? This material is very intriguing. It has a lot of unresolved mysteries in there. It has a large hysteresis curve, for example. On the right-hand side, you see 2 hysteresis curves at 2 different times of its life. And as you're charging at a slightly higher voltage than you're discharging. And the big question is, what are the structural changes between 2 points on that hysteresis curve at the same state of charge versus the same voltage? And can we learn what kind of defects are being created in there? This is a work we do very, very closely with Argonne National Laboratory together. They're doing essentially a lot of the spectroscopy on it, a lot of the electrochemistry on it. Brookhaven does a lot of the X-ray diffraction on it, and we're doing a lot of neutron diffraction and magnetic susceptibility on it to understand really where the oxidation states of the materials are going. And without going too much into detail, I wanted to just show you a couple of intriguing things where we're slowly able to understand what is the structure at which times. We have no clue yet how to solve it, but we at least understand slowly what is happening in there. And there again, some neutron diffraction patterns which allow us to see our ions sitting where they are supposed to sit. So this is not the nickel-lithium swap. This is where lithium all of a sudden sits in a different site. And in this case here, if you just look at your pattern and you model your regular structure with no defect in it, again, that peak marked here does not fit your experimental data. As you start putting your ions into tetrahedral sides and you start fiddling around with that, you make it fit. So you can determine where are your atoms sitting at which time. And you can see how are my ions floating around here. So we're constantly looking at nickel and manganese, for example, getting into lithium sites, stealing us capacity, as well as messing around with our voltage on that material. The same thing is on phases, essentially on there. And I will skip through that to not bore you too much with those details. And I want to skip to this slide here to show you essentially that a lot of the activities we're doing is directly with industry. We're having a large number of battery manufacturers, equipment manufacturers, material suppliers, and end users in our portfolio of collaborators to really try to build a domestic supply chain for battery manufacturing here in the US and be able to move these materials as we study them into the marketplace very quickly. With that, I want to thank you all for your attention, and I want to thank the contributors to this work. And these are just the people who contributed to the results I've shown here. The total number of people in the program is much larger. Thank you very much. If there are any questions, I'll be happy to answer them.
Tesla has just announced that they're going to be building this gigantic battery plant that's supposed to produce more lithium-ion batteries than all the other plants in the world combined. Are they coming to you to find out about this technology that might reduce their cost by 15%?
I'm actually, I'm afraid Elon Musk would hire our people on there. He's not known for good collaborations, right? He does his things alone. So But yeah, no, we're not in collaboration with them at this point. But it is a very intriguing development because up until Elon Musk announced this plant, everybody thought like we will not see a new battery plant in the US for the next 10 years at least, because we're currently having a several-fold overproduction in the US. And battery plants are struggling to survive. They're looking for new investors. Right? A123 went bankrupt. Dow Kokum was sold. Johnson Controls can only survive because they are able to sustain a continued loss in that market because of their large other portfolio they are selling. It is quite amazing. Now, my question in that regard is, have the other companies done something fundamentally wrong, and Elon Musk could make it right to essentially get a large portion of the market from Japan and Korea into the US? That's really his goal in there. Now, it also tells me the big problem we had so far with our processing research was that if we're suggesting a change in processing in order to reduce cost, it would come on the back end of those investors having made large investments in capital equipment already. And they have no way of recouping that money right now. So we're seeing a lot of pushback on changing things in the manufacturing side. Now, with new plants being created, that might change, right? Things are opening up. Several projects we're having are being considered right now by a number of battery manufacturers for inclusion in a next generation plant if they would be able to expand those plants. New methods of drying, for example, new methods of removing water, which is gathered out of the air in your product and you need to get it out before you seal your device, things like that. Yeah. So I would buy stocks if that's available from him. They do. And that is essentially all in the EV Everywhere blueprint. So if you go on the web and you Google for EV Everywhere, you'll find that. It's a very short 8-9 page PDF document which describes not just the battery but also the power electronics and other components on where do they need to be when to meet our targets. I'm not sure if I recall the range right away. But the goal, so what they're doing now is they're essentially stepped away from defining too much of a system. They say we want to be able to provide the components which allow you to distribute that technology cost effectively. And they're going in an ownership cost model. They're going to a metric they call penny per mile rather than dollar per kilowatt hours of energy, because that's something people don't understand. Penny per mile they understand. They know how much it costs right now to drive a mile. And the idea is, can you sell a car, own that car for 5 years, and then get rid of the car, and your driven mile is as competitive in price as the gasoline, the pure gasoline cousin. That's essentially the goals. And that is driving the agenda quite dramatically. So we have goals set for 2020 and 2025 in that regard. And some of the cost models I showed on the 4 different battery types is stemming from those goals, right? They're extrapolated from those goals. Now, where are we in terms of the current battery technology? On regular lithium-ion batteries, we can improve cost. And then switching on to advanced lithium-ion batteries, where we have better cathodes, higher capacity cathodes, higher voltage cathodes. So for every electron transferred, you get more energy. And then going over to high capacity anodes, those 3 combinations, we believe, will allow you to meet the EV Everywhere targets. If you then want to go even further and increase further electrification to allow a deeper market penetration as you move forward, or make even electric vehicles more competitive, if you will, then you would probably need to go towards other advanced chemistries. Now, those are very questionable still because it's on the research bench scale right now. Yeah.
Is there any focus at all on possible applications to general aviation? Weight would be a consideration for that in the amount of available power.
So you mean running a passenger airplane electrically?
Well, a small plane.
Yeah. I have not done the detailed calculations on that. A typical gut reaction I see when people are starting to think about that is that the total amount of energy is huge there, right? I mean, if we look right now, the amounts of jet fuel we're having in an airplane are gigantic. And it's burning a lot very quickly. So I would have to look into that to get a better answer than in just this qualitative statement. But DOE is currently not looking into that. That's a short answer.
I'm curious in terms of grid applications. The work you're doing here is heavily on transportation. That's one thing. How much does that translate over to perhaps grid applications, or do you see those as separate markets with different characteristics?
So on grid application, actually, in some high-value applications, you already see lithium-ion battery in the grid applications as well, right? The big problem, the biggest problem is typically the high voltage generates a lot of energy. That's great, but the high voltage also introduces some issues which limits your opportunity to size individual cells. So, for example, on a lithium-ion battery, if you have a 60 amp hour battery or a 70 amp hour battery, those are really large batteries. People are afraid of going any larger than that. That now has a result that if you want to store large amounts of energy, much more than what you would need on a car, something for, let's say, backup storage for a photovoltaic power plant, right? To go through the night and to go through the cloudy times and so, you need a large number of cells you put together. And there's a problem that cost does not scale very well on that side. So economies of scale don't fit as well, and you don't see the cost advantage of going to bigger and bigger cells as you see with some other technologies like redox flow batteries, for example. So for specific applications where you can allow a smaller amount of energy being used and a higher value product being delivered, there it is a good alternative, and it is in use. We see some tests from some utilities on neighborhood scales for backup powers to make sure they don't have outages. We see some things where they have a small number of trailer-sized storage at substations, for example. Things like that are possible. Yeah.
You see anything with major automakers with strengths that you mentioned with limited range, cost, them continuing to develop using battery technology or looking for other alternative sources of power?
The great advantage of batteries is that we don't need to reinvent our infrastructure, right? That is why I believe right now we see that push and we see the acceptance from the car makers for that technology. Other technologies often require a change in infrastructure, which is much more dramatic than what we see with batteries. The big question is, are we able to make a battery a full replacement? That is not possible without big infrastructure changes. And I think there in the future, it is not decided yet what would be the technology moving forward, right? So the battery technology is very good for commuter vehicles. It is very good for delivery vehicles. It is very good for short ranges, right? It is not very good if you want to do a cross-country trip. And that's where it stays to be seen if battery technology will develop further so that you could do that. If our wireless power transfer on the power electronics, what Burak talked about, will develop to a stage where you could have electrified highways and you can downsize your battery and just cover the last, essentially make any trip a commuter trip or just a short range trip as soon as you get off the interstate. Or if you require other alternative technologies, fuel cells, any type of short-term biofuels, right? What you want to try to do is you want to diversify your energy sources, and you want to reduce the long-term carbon footprint, right? And any one of those technologies does definitely the carbon footprint thing. Diversifying the energy sources is somewhat possible with the hydrogen economy. It's definitely possible with the battery technology on board. Stands to be seen.
What sort of impact do you see with changes in battery technology having once they enter the waste stream? Are recyclers of that technology set to handle the changes in battery technology, or are those things we're developing along with the improvements in battery systems?
So the DOE is looking at that as well. The DOE is actually funding several recycling companies to develop that. So far, the problem was the materials, even though the battery is expensive, it's still too cheap at this point to justify recycling on an economic scale because it's cheaper to get new materials then. But scientifically, there's no reason why you could not recycle. Every single item in there you could recycle. We see more push towards recycling on the European market, where they have higher regulations in terms of how much of your car needs to be recycled in order to be legally sold. There we see much more push for that. Another big opportunity we're seeing for the battery side is also a secondary use option. Where, remember, the vehicle application is a very demanding application. You're very limited in your real estate on there, which essentially puts very stringent limits on what does end of life mean. Your cell phone has a much wider window than your car. As soon as you reach 80% of the initial capacity left, it's considered to have reached its end of life. So that means when you're 100 miles, only get 100-mile range drops down to 80, the people are expecting the battery to be exchanged. Now that is still a very high energy dense device, right? If you compare it to any other commercially available battery technology out there, that device has a higher energy density still than anything else. And so one could think about putting that in grid applications, for example, where all of a sudden your cost calculations become much better. Now the tricky thing is how to forecast all of that, because we don't have large amounts of batteries available yet. That's where we will see if entrepreneurs will be able to utilize that opportunity.
You mentioned carbon footprint. Just how does the total life cycle cost of you're going to generate electricity in this country, much of that from coal? How does that, plus the mining of lithium, how does the total life cycle cost work out for battery technology?
So the use cycle is very favorable because you can typically generate electricity much more efficient than you can run a small internal combustion engine. The full life cycle cost, I'm not exactly sure on that. Actually, DOE has some studies on it, and I should have made my homework and looked that up before, because it's very likely that a question comes up, but I'm not exactly sure on that. And the question is really how much energy goes into a battery versus how much get you out over the lifetime. Now, one thing, remember, on the battery side itself, it's a reuse product, right? You're not consuming stuff in the battery. You're reusing it, right? You're charging and discharging. That's how it works a little different on its calculation than petroleum, for example. There was, for example, there was a study from UT, when was it, about a year ago, where they were looking at a particular region in China where there was a high concentration of coal-powered plants. There, I think the carbon footprint was about the same still, but the particulate footprint, the smog developed essentially, was much worse for electric vehicles than for pure gasoline vehicles because of the lack of scrubbing in the coal power plants, for example. So it definitely depends on how you produce the electricity, but typically efficiencies pan out that in this country with our regulations and technology we have, as well as in most parts of Asia and all of Europe, it is favorable.
So we're at the 11 o'clock, and I want to respect everyone's time today. I know their meeting's not so long, but let's thank Claus one more time for.
Thank you.